Okay, let's talk about discontinuous functions. When we're talking about derivatives, we have to worry about the fact that functions are continuous because we can't find the instantaneous rate of change at somewhere where the function doesn't exist. But it turns out in certain cases, we can find the area under the curve of a function regardless of whether it's continuous in certain cases. So let me show you a couple examples of what that would look like. Let's first look at this function here. The integral from -1 to +2 of absolute x over x dx. So the area under the curve between -1 and +2 of that function. So let's think about this function a little bit. If I have absolute x over x for x greater than 0, then this is just going to be equal to 1. Absolute value of positive divided by the same positive. If I have absolute value of x over x for x less than 0, well, the numerator becomes positive, but the denominator stays negative, and so this becomes -1, which means that this function graphing in the region of interest is going to look like this. And it's going to look like this, which means that we can see that this integral is just going to be equal to 1. Notice, just a reminder, because you were thinking 3, that's +2, but this is -1, and so when I put them together, I get 2 minus 1, which is 1. And of course, notice that this function is not defined for x equals 0 because that would be 0 divided by 0, which is undefined. All right, so there's one example. And you can go ahead and check this in your calculator. If you look at the math menu on the TI-83-4 platform, and then arrow over to the number menu, you'll see that the very first thing is ABS. And that will pop up as either ABS parentheses or as absolute value with a little rectangle for you to type stuff in. All right. You also may notice that when you plug this into your calculator, you get 1 point something. And that's because it's approximating, and it's splitting. It's actually doing the Riemann program to do these approximations, and it's not necessarily going to be exact because of the way it splits these up. All right, if you're in my class, go ahead and do exercise 41 in the book, and then come on back, and we're going to do a little exploration here. All right, So what I'm going to ask you to do on this exploration is, as I introduce each question, pause, take a few moments to think about it, and then restart the video. So let's start with question number 1. F of x equals x squared minus 4 over x minus 2 on the interval 0, 3. And the question is, why is it not continuous, and what kind of discontinuity do you have? So go ahead and pause. Why is it not continuous, and what kind of discontinuity does it have? And if I look at this function, what I see is that that's a perfect square on top. And you're all thinking, no, that's not it at all. Of course not, it's 2. And an x minus 2 on the bottom, and of course we know that that thing right there is a hole in the graph at x equals 2, which means that we have a removable discontinuity. So what does this equation or graph look like? Well, f of x is equal to x plus 2, except when x is equal to 2. So now what I want you to do is I want you to draw a graph of this function, and I want you to use area to show that the integral of this function is equal to 10.5. So go ahead and draw yourself a graph, calculate the area under the curve, and come back. Okay, so drawing the graph, we've got x plus 2 looks just like this. From 0 to 3 looks just like this. We have a trapezoid with a height of 2. Excuse me, not a height of 2. A base of 2, a base of 5, a height of 3. So this is base 1. This is base 2, a height of 3. And we all remember, of course, that the area of a trapezoid is the sum of the bases halved times the height, which is in fact 10.5. Good. Finally, I want you to find the integral from 0 to 5 of the floor function int x dx. And I want you to, again, also find this using area. Just a reminder that int just rounds down to the nearest whole number. So go ahead and draw yourself a sketch. Think about that a little bit and show using area that that integral is equal to 10. All right, welcome back. If we graph this function, here's what we see. Is that everything between 0 and 1 rounds down to 0. Everything between 1 and 2 rounds down to 1. Everything between 2 and 3 rounds down to 2. And so looking at this, I have an area of 1 here. I have an area of 2 here. So I'm up to 3. And this is 1, 2, 3. The next area is clearly going to be 4. Whoops, excuse me. This is clearly going to be 3. And the next area is clearly going to be 4. And when I sum those, I get 1 plus 2 plus 3 plus 4, which is in fact 10. So confirmed. All right. Great. Thanks for watching.